Hey guys, I just wanted to make this very quick video to explain a sort of a nuance, which I think I originally tried to point out during the lecture yesterday, but it might have gotten deleted when I was like editing it, or I don't know. And then I kind of actually ended up making this mistake myself later on in the lecture. So, but I want to make sure everyone is totally aware of this distinction because it's something that actually affects proofs sometimes, and it's really easy to overlook, like when it can be an issue, I guess. Okay, so the issue here is that we're talking about we had this theorem 11.2, which says that there's a subsequence of Sn converging to T when the set of N, where Sn is in T minus epsilon, T plus epsilon, is infinite for all epsilon greater than 0, right? Actually, this is, so if and only if, right? That's part of this theorem. But the thing I really want to highlight here is the fact that this set is actually a set of indices and not a set of values, right? I mean, rather, this is not Sn, it's just the N, right? And so why would this be important, right? It's important because actually, if you think of a case like, consider, -1 to the N or something, right? Then clearly, there's a subsequence converging to 1, say. The set of N for which, -1 to the N is in, let's say, 1 minus epsilon, 1 plus epsilon, for small epsilon, let's say, is, the even values of N. So, right, which is clearly infinite. But the set of, Sn, for which, let's say, yeah, the set of values in the sequence which are in this set is just 1. It's a singleton set, right? This is not infinite. So basically the issue is that there can be repetition of the values, which make it so that, well, really there can be a repetition of the value T itself, which could constitute a subsequence converging to T, even if there are very few other values of Sn which actually fall in this interval. In fact, possibly only finitely many, right? So subsequences, if there's a subsequential limit, there doesn't actually have to be a cluster of different values of Sn around the limiting value T if there is, if T itself gets repeated infinitely many times, okay? So that's kind of an important subtlety. And this actually, I kind of made this mistake myself, although it doesn't affect the argument, which is why it's sort of like, it's easy to make this mistake when it's not, even for, someone who's sort of practiced with material, it's easy to phrase things incorrectly when it doesn't really matter. I would not make this mistake myself in a situation where it actually mattered, but in situations where it doesn't really matter, it's easy for me to slip up with the phrasing. So, my apologies for that. So let me explain this mistake. So it was in the, well, here, let me just clear everything. So it's in the proof of the very last theorem, which was about, you know, showing that, so let Sn be a sequence, S the set of subsequential limits, then S is closed, i.e. if Tn is a sequence of values from S and Tn converges to T, then T is in S as well. Okay, that was what we proved. And our strategy, remember, as I wrote it, was to show that the set of Sn, right? I think I wrote it like this. So T minus epsilon, T plus epsilon intersect Sn like that is infinite for all epsilon. This is actually wrong, right? Because here I wrote the set of values. So really what we should write, let me, the way we should describe this is, here, I'll just rewrite it in red. What we really want to say is the set of n for which Sn is in T minus epsilon, T plus epsilon, just like it says in the statement of theorem 11.2, right? That's what we wanted to show was infinite, not this other expression, because this might not actually be infinite. If the value T gets repeated infinitely many times, this is actually allowed to be a finite set, okay? So that's all I wanted to clarify. Apologies for the error, but hopefully this makes things clearer.